Okay. Um, Welcome to lecture 17. Last time we did studied some exotic properties of fermionic integration, and today I'll use those properties to actually do fermionic path integrals. And so what we want to do is to introduce a variable psi of t, which you should think of as one component of a Dirac fermion field in the ultra-local limit this word means independent of x. It means we are taking a field and pretending that there is no space at all of space is one point. So therefore the function is just a function of t, and it's much easier to do path integral for that, and for introducing x dependence it's not a big step. It's a big step in the impact, but for the formalism is quite clear, and we did it already. We studied path integrals for x of t, which was interpreted as a coordinate of a non-relativistic particle, and then we quickly generalized to phi of t and x. We'll do something similar here, except that psi will be anti-commuting, and it doesn't have an obvious interpretation, but there is actually an physical interpretation which we'll discover in a few minutes. So in canonical approach, we quantize this by saying that psi with psi dagger is equal to 1 at equal times, and psi with psi is the same as psi dagger with psi dagger is equal to 0. All these things are operators and they have hats. Okay, and we want to calculate the analog of a propagator where we start with the Grassmann value or odd anti-commuting value psi 0 at time t0 and propagate using the Hamiltonian to psi n at tn. But because this is a what is this one called, bra vector, the psi appears conjugated. We'll see the precise definitions of these states and you'll understand why I write psi dagger. And I'm going to write this as a normalization times psi n dagger Tn, the field eigenstate, e to the minus IH T psi 0 T0. This n will be a normalization, and the reason is that we'll define these in a way which is naturally not normalized to 1, and then n will come in to make them normalized to 1. Okay. And of course capital T is Tn minus T0 as always. And the definition of these states is as follows. So we say that the operator psi acting on psi 0 T0 should be equal to the eigenvalue psi 0 times psi 0 T0. You see there are lots of anti-commuting things around here, but when it doesn't have a hat, it's just an anti-commuting number, but when it has a hat, it's actually an operator. And that's also anti-commuting by these relations. Okay, good. Okay, now the nice thing is, in the case of x of t, to define this we had to use some delta functions, but here it's actually much simpler. And this is a very beautiful and simple feature of these anti-commuting operators, or fermionic operators as we call them, which is that we can define the full space as a Fock space, but a much simpler Fock space than the one that arises for the harmonic oscillator problem. And so we start by saying, let's define a state 0 by saying that psi hat on 0 annihilates it. This is like we are treating psi and psi dagger just like we treated the A and A dagger in the harmonic oscillator problem. So we do this. One side comment is that in the harmonic oscillator problem, the original variables are P and X. Then we take P plus and minus Ix, and then we get A and A dagger, and then we do this. But in this problem, the original variables are psi and psi dagger, and they are already the oscillators. So in some sense, this problem is given to us in oscillator form, which is quite nice. I haven't yet specified a Hamiltonian, but given these commutation relations, we can find the structure of states. So we define this. Then we define another state 1, which is equal to psi dagger on 0. So psi dagger is a raising operator and brings the state 0 to the state 1. But now the best part is that's all the states of the system, because if we try to act with psi dagger again, then we'll just get 0 because psi dagger squared is 0 by this relation. On the other hand, if we try to act on 1 with psi, then we'll get psi dagger on 0. Then by the commutation relation, this one, I can interchange them, and so I'll get eventually, let's check it, psi on 1 is equal to psi dagger on 0 is equal to 1 minus psi dagger psi on 0. But psi on 0 is 0, that's what we started with, so this is just equal to 0. So psi dagger takes me from 0 to 1, and psi takes me from 1 back to 0, and that's the whole system. And now we realize that actually psi describes a spin-half, non-relativistic spin-half system, otherwise known as a two-state system. And that's what it's doing. So it's just a two-state system. The states are 0 and 1, and psi and psi dagger take me up and down. It's the analogy with spin is that if I have a spin half particle, then it can have two states, spin up, spin down, and the raising operator of spin takes me from down to up, and the lowering takes me from up to down. So end of that. So that's how simple it is. Okay, good.
So,
yes.
how did you make the comment that these are oscillators?
No, so I'm saying that they behave just like oscillators because of they are conjugate to each other, just like A with A dagger, and the only new thing is that this is anti-commutator instead of commutator.
Right, but we get the ladder part of the operators from the fact that it commutes with, like the commutation with the Hamiltonian has that eigenvalue shifting up and down, that property.
Yes, so we haven't yet specified a Hamiltonian, but whatever the Hamiltonian is, if once I define psi on that there is a state psi 0 such that psi on 0 is 0, the only other state in the problem can be 1. There are no other states. Now we'll associate, we haven't said anything about their energies, that will come as soon as we specify the Hamiltonian. But in fact, specifying the Hamiltonian will take exactly 1 second, if I can find the eraser, because we just copy what we learned in the harmonic oscillator case. It should just be proportional to the number operator, and the proportionality should be some number, which a parameter, which we can call the frequency. So H will be omega psi dagger psi. And psi dagger psi is again the number operator, just like A dagger A in the case of bosonic operators. And this number operator in this case has only two eigenvalues, 0 and 1. Okay. Now we could add some, we could have, so we'll keep omega right now. And we see that H on 0 is just 0 because this annihilates 0. And H on 1 is just omega on 1. Okay, because I told you psi dagger psi is a number operator. On 0 it just gives me nothing, and on 1 it gives me 1. So I get this. So that means my two energies are E0 equals 0, E1 equals half. Sorry, equals omega. And omega means H bar omega. So I've set H bar equals 1, but you can always put it back. And so it's two states with these two energies. Now this suggests that probably we should have done something more clever to call this omega minus half in that case, E0 would have been minus half, and right? Sorry, minus half of minus omega by 2, and E1 would have been omega by 2, which is a little more symmetric. Just we would shift the operator by half. And again, this is reminiscent of, am I saying the right thing here? I'm a bit confused. N plus half. No. I think I want to just shift by overall half, not half here. Yeah. That's what I want to do. And minus omega by 2. Huh? Minus omega by 2. So it's actually psi dagger psi. I'm shifting by half. Sorry, this is what I wanted to write. So this is exactly how I shift the. So this is very much like the 0-point energy of the harmonic oscillator, but that's required to be plus. Here, minus is a convenient choice. It gives a symmetric spectrum. But I won't worry about that shift for now. Just you should keep it in mind that it's a possibility. So right now we'll just keep it like this. Okay. Good. Now, yes.
Here you are representing one particle state, right?
Yeah, I mean, you can think, yeah, that's right. So it depends how you want to interpret this. If you interpret it as a spin system, then there's always a particle, and the spin can be oriented in two ways. If you want to interpret it in field theory language, then this is the empty, this is the vacuum, and this is the one particle state.
For two particle state, I need one more psi.
See, you can't have a two particle state because of this ultra local limit. Because there are no points in space, and Pauli exclusion doesn't allow you to have two particles at the exact same point. So there are no two particle states in this system.
Space coordinate.
Exactly, because of that.
Okay.
That in case of x of t, we could have still had multiple occupation of the same state. Here we can't have that. Or there we could have acted with a dagger many times. Here we can't do that. So this is everything. But when it becomes field theory, then of course there will be more states. Then this space is not going to be like this. This is all special to the ultra local limit where everything is simple. Yeah. Yeah. Okay.
So this is true for two oscillators also.
For what?
Two oscillators. If we consider two oscillators.
You mean two psis?
Yes, sir.
With an index? Yes, you could do that. But then you will have four states because there will be two psis and two psi daggers. So each psi dagger can create a state. And then both psi daggers can also create a state. So there will be total four states. 0, 1, 1 prime and 2. That will be their energies. 1 and 1 prime will be the degenerate states. If I give the same frequency to the two oscillators. If I give different ones, then I'll get energies 0, omega 1, omega 2 and omega 1 plus omega 2. But it's not very interesting because it's just the square of this system. Unless I put some interesting couplings in the Hamiltonian, it won't be very interesting. Okay. And the partition function of this theory is of course very simple. It's trace of e to the minus beta h, and this is equal to 1 plus e to the minus omega beta, because the eigenvalues of h are 0 and omega. So that's the full partition function. Good. And in the symmetric form, if I, after a shift, it would become e to the minus omega beta by 2 plus e to the omega beta by 2, which is twice cos omega beta. So these are equivalent. All we've done is shift the 0 point of the energy by hand, and we go from this function to this. Both of them have the feature that the excited state to ground state spacing is this, is omega. That's the only thing that we really by cos omega beta by 2, absolutely. Good. Okay, so that's all clear. Now we need a little bit more detail. So these states we have defined are the energy eigenstates 0 and 1. We want the position eigenstate. So we want a state such that psi hat, when acting on psi 0, I'll drop the t, but there's always a t associated to it. Its eigenvalue should be psi 0 on the state. How do we construct such a thing? just using the 0 and 1 states. It has to be, every state in this system is a linear combination of zeros and ones. So it can't be very difficult. Okay, so the answer is that the state psi 0 is equal to 0 minus the number psi 0 times 1. And it's very easy to see what happens. If I act with psi on this state, psi when acting on 0 gives me 0 by that first rule. When it comes here, it has to first jump through psi 0, which is a number, giving me a plus sign. When it acts on 1, it gives me back 0. So I end up with psi 0 on 0. But psi 0, okay, let's do it. I think it's better to do it once. Psi on this thing, just check, we are checking. On 0 minus psi 0, 1. This is equal to, this is 0, so it's minus psi on psi 0, 1. This is equal to psi 0 on psi 1 by interchanging them. This is equal to psi 0. Now psi on 1 is 0, so this psi 0 on 0. And this doesn't look like an eigenstate because I started with psi hat on this whole thing, and my answer is psi 0 only on 0. But psi 0 on 0 is the same as psi 0 on 0 minus psi 0, 1, because psi 0 squared is 0. Now you can see it's clearly an eigenvalue equation. Psi hat on this state is the eigenvalue psi 0 on the same state. And so I've constructed psi 0. Okay. And I can easily construct the dagger of it. Okay, sorry, I hope that wasn't too fast. I shouldn't rub it out. Anyway, it's in your notes. Since I rubbed it out, let it go. Okay, good. So, likewise, the final state psi n, which I want to use in my, so I'm propagating the fermion from psi 0 to psi n. So, this turns out to be 0 minus 1 psi n dagger. This is the dagger of that, and with 0 replaced by n. Okay, and that's why, so this state I'll call I called it psi dagger, because now if I act on the right of this with psi dagger, the eigenvalue will be psi n dagger. Good. Okay. Now an interesting thing happens. If I take the inner product, so I should check whether these position eigenstates are normalized. So I should take the product psi 0 dagger psi 0. And what is this? This is for psi 0 dagger, I put this with n replaced by 0. And for psi 0, I put that. And when I collect, now I take the inner product. So 0 comes with 0. 0 is orthogonal to 1. So there are no cross terms. 0 comes with 0, that gives me 1. And this term, psi 0 dagger psi 0 with a plus, and then 1 with 1. 1 with 1 is 1. So those are assumed to be normalized. So I finally get 1 minus, or 1 plus rather, psi 0 dagger psi 0. And this is an example of something I had been saying yesterday, that you can have an ordinary number added to a commuting Grassmann number, which is made by a even number of size. So this is the answer. And now, of course, this is the same as exponential of psi 0 dagger psi 0. So that's also a nice thing. And that shows that the normalized state, therefore normalized state, is not this one that I defined here, but it is e to the minus half psi 0 dagger psi 0 psi 0. Okay, this in turn implies the relation that integral d psi 0 dagger e to the minus square of that on psi 0 is equal to 1. So the unity which we would expect by integrating over all size, we expect this position states to span the by completeness. If we integrate over all of them, we should just get 1, and we do, but because they weren't normalized, we won't get 1 unless we stick in this factor. Okay. So now for the quantity we want to calculate, we said there's a normalization factor, and now we know what it is. So the normalization factor is, so the quantity we want, which we called u earlier, is n psi n dagger at time tn e to the minus iht psi 0 t0. And this n now is the one which normalizes this state and also normalizes this state. So it's a factor of that, once for psi 0 and once for psi n. So curly n is equal to e to the minus half psi 0 dagger psi 0 minus half psi n dagger psi n. And we'll bring it back at the end when we need to discuss normalizations, but for now it will just hang around. Okay, so I might forget it when I do calculations, right? You see that what I said here is that this is a normalized state. Okay, so that's why I put this in here, and likewise for this to be normalized I need to put this here. You don't seem very happy with something.
No, I was thinking there would be a plus sign when you do the
No, there isn't.
dagger and
No.
because then you have to switch.
No, there is not. And why is there not? Because psi 0 dagger psi 0 dagger is equal to, starting from the right to the left, psi 0 dagger psi 0. So it's unchanged under dagger, which is just as well, because remember that's how the Hamiltonian is made. Hamiltonian better be Hermitian. We don't want i's in the Hamiltonian, and this is this is because of the rule that dagger means start from the right to the left, like with matrices, and dagger everybody. Okay, good. Okay, good. Now the path integral won't be very difficult with all these rules. So what we are going to do, so we are going to now forget this n. You will just have to remember that n is what I wrote, and we are just going to leave it and put it at the very end. So now this thing will be equal to the product. I'll write it and then I'll explain. It's something you've seen before. So I break this U into, by inserting complete sets of states psi A, where A goes from 1 to n minus 1 at the n minus 1 intervals along the time axis. Okay, so each interval is some epsilon, which is the total time divided by capital N, and this will be the normal to normalize each of those. So I'm just using this relation that this is 1 for all of them. And then once I insert it, say somewhere here, then I'll get the u for the thing on the right, thing on the left, propagated by a time epsilon, and that's exactly this. Okay, and
integrals, right?
say again.
Some integrals for the
Integrals. Of course, there are integrals. There are integrals over all these. These are the integration measures. Thank you. Yes.
So,
Yes.
how exactly do you decide whether d psi dagger or d psi should be placed first? Like,
Yeah, I personally decide by forgetting it and making mistakes every day. So there's no, I'm not following any consistent rule in my life, what I've got here. So they must, of course they are not the same. This and that are just minus of each other. So I don't know what to do. I should look to my notes for some guidance, but I think my notes are maybe here. Let's just hope that this works. It's just a minus sign, but minus signs are important in this subject. So we'll see what happens. Okay, now what is that u? Well, it's going to be, this u is going to be by definition the same normalization factor, but b comma b minus 1 times psi b tb e to the minus I h epsilon psi b minus 1 tb minus 1. Okay, and here I'm going to insert a complete set of energy eigenstates, the 0 and the 1. So here I will put 0, 0 plus 1, 1. And when I do that, then the Hamiltonian will automatically get evaluated on when it's sandwiched between these. So it hits this 0 and gives me 0. When it hits 1, it gives me omega. So the answer of this will be this n psi b tb dagger, then 0, 0 plus e to the minus I omega epsilon 1, 1. And then I complete it with the state on the right, that one. Okay, so I evaluated my Hamiltonian, and here it didn't give anything, and here it just gave this infinitesimal factor. Okay, and now I can take these inner products, 0 with psi b dagger tb, 0 with psi b minus 1, similarly for 1, and all the inner products are dictated. For example, 0 with a psi is 1, because it doesn't count this term, it only counts this term, and 1 with a psi is psi 0 up to a sign. So I know all of those answers, and so if I work it out, it's all written in the notes, and you learn it best by doing it yourself. But if I work it out, it will be this will be equal to n 1 plus e to the minus I omega epsilon psi b dagger psi b minus 1. You can guess where they come from. 1 comes from this term, which simply projects out a 1 from both sides, and the e to the minus omega I omega, on the right side this 1 pulls out the number psi b minus 1, and on the left side it pulls out the number psi b dagger. So this is it. Okay, now good. So in the end we have putting everything, actually, so I don't know why I kept this n. I think these nb b minus 1 just come from this. I'm basically dividing this up. So this is there at every point that I'm integrating, every one of n minus 1 points. But I take half of this for psi b and half of it for psi b minus 1, and that's my n. Okay, it's pretty easy to account for. So finally at the end, u that I started with is equal to integral d psi dagger d psi product e to the minus psi a dagger psi a. This is that factor, and then this factor, which I am going to rewrite as product b equals 1. This was also a product, I guess, or this was just This was just a single u, and so there's this product b equals 1 to n, and I have to put this factor in. But this factor I'm going to write as okay, so right now I'll write it as it is, e to the minus I omega epsilon psi b dagger psi b minus 1. Okay, this is correct.
So the NB,
Sorry?
NBB minus 1.
The NB. N is, so all the n's are collected in here. So I can either write this product or I can write each NB. So it's, maybe I'm doing a little bit of a, sorry, I think I was doing a bit of a hybrid thing.
But doesn't every amplitude
Yeah.
come with it a normalization since the kets are not normalized?
Yeah. So, okay.
So there will be a pi of NBB minus 1 or all the.
Yeah, there is actually. And that's, I think, why it turns into half. Let me just try to do it, and I'm probably going to get myself confused before the end of the lecture. But let me try to write the answer that I have, because I did work it out once. NBB minus 1. So this n is e to the minus half psi dagger b psi b and minus half psi dagger b minus 1 psi b minus 1. So you're asking whether I want this as well as that. Yeah, so maybe here it's still there, but in the next step it will go away. Let me write what this should become. So this should become integral product over a d psi a dagger d psi a. Now this I'm going to take inside and write it as e to the minus psi b dagger psi b. So this was product over a of e to the minus psi a dagger psi a, but here I have a product over b's, so I can just put it inside. But there's a small mistake I'm making, because the nth, b has an nth one, but a doesn't have an nth one. A only goes to n minus 1. So here I have a term e to the minus psi n dagger psi n, which I shouldn't have. It wasn't there. So I'll compensate by putting the opposite term outside, and it's what is called a boundary term. Okay, so far so good. And now this factor I'm going to exponentiate as e to the 1 minus I omega epsilon psi dagger b psi b minus 1, and the error is going to be of order epsilon squared. So what did I do? I just wrote this as exponential of this much, and this much, this e to the minus I omega epsilon is same as 1 minus I omega epsilon plus higher terms in epsilon, which I am dropping. Okay, and there are no more terms, so I think this n has been absorbed somehow, and
So there is still an n outside, right, which we are not.
that n outside is there. That n outside is
That
always
is for 0 and n.
Yeah, that is only for 0 and capital N. Yeah, I'll try to write the notes to explain this apparent inconsistency of putting NBB minus 1 on the way. I think the reason is, I think the reason is there's no NBB minus 1. If I write this with u's, then this should not be there. So this is correct where u is the normalized one. Okay, because it's the normalized one where I can insert with a complete set of states at each thing, right? Those are the ones which satisfy the composition law. Composition law is not satisfied by unnormalized or randomly normalized objects. We stressed that in the beginning. So for correctly normalized objects, we just have to integrate them, nothing more. Okay, but because u is this times this nbb minus 1, so I have to keep this 1 for every pair b minus 1b, and when I accumulate them all, then I get this factor. So the product of all the nbb minus 1s is exactly that factor. So that's why I don't have to write the nbb minus 1s anymore, and I have this.
So in the end,
Huh?
is that 1 minus I omega n?
Yes, it's 1 minus, it's this. So I did two steps. First, 1 plus something times psi dagger psi is exponential of this thing times psi dagger psi. And then this thing I approximated by 1 minus I omega epsilon because epsilon is small. That I could not, that's not because of Grassmann nature, that's because I'm breaking my path integral in small steps. So that's the next level of approximation. And now I can collect everything. So now I have got all my stuff inside, and you see what's happened very nicely. Minus psi b dagger psi b and plus psi b dagger psi b minus 1 is going to give me psi dagger psi dot. Infinitesimal amount of psi dagger psi dot. So this is actually going to be, this is equal to e to the psi n dagger psi n integral product and then product. So now this product, since everybody is in the exponential, this product will become a sum in the exponential. I don't have to write it as a product anymore. And what's in the exponential? It is e to the I summation b equals 1 to n I psi b dagger psi b minus psi b minus 1. This term is coming from this and this 1 times this. And I put two i's to make this minus sign. So one I stays out and one comes in the Lagrangian. Yes?
The normalization will give me either minus psi n dagger psi n in the first step.
In which step?
In the first.
Here?
Yeah.
No, this factor comes from accumulating all the n b
But
b
there
minus
is
1.
psi n also there. Right?
Psi n, that there's an overall n normalization that I have kept. So that n was equal to e to the minus half psi n dagger psi n minus half psi 0 dagger psi 0. It's always there, and I'll just multiply it at the very end because it doesn't participate in this calculation. Okay, so that's this term, but this term does not have any epsilon in it. Okay, and the other term then is minus. Now I has already come out, so it's omega psi b dagger psi b minus 1 epsilon. Is that okay? This is e to the plus I omega. Oh, and I have here minus I omega. Did I change my sign? I should have minus. This looks correct. What did I do wrong here? Anyone? No, so it's correct. I took out I from e to the minus I omega epsilon. So e to the I, so I have only minus omega there and epsilon. That's correct. Okay, and now it's very easy to see what we are supposed to do. There's an epsilon here, there's no epsilon here. So I'll divide this by epsilon, and multiply by epsilon. So there's an epsilon in both terms, which I'll take outside. Okay, and now in the limit, you can see that psi b minus 1 over epsilon, that means psi at one time minus the previous time over epsilon, goes into psi dot. So this quantity goes to I psi dagger psi dot minus omega psi dagger. Now it's little embarrassing that here we have b minus 1, but again we can replace psi b minus 1 by psi b with error of order, higher order in epsilon. So it's just psi dagger psi, and the whole thing multiplies dt, which is that, and this thing is LDT. So I found my Lagrangian. I didn't know what Lagrangian I should have got, but I found a Lagrangian, and it turns out it's the right one. Actually, you can more or less see it's the right one, because imagine the Dirac Lagrangian. Forget about all gamma matrices, just forget about them, forget about all space derivatives. Then that's the Dirac Lagrangian, with omega being the role of omega being played by m, the mass term of the Dirac field. So it's actually a correct Lagrangian. And in fact, you can go from this back to the Hamiltonian by noticing that the conjugate momentum to psi is psi dagger. And so the PQ dot minus L term kills this, and we are left with this with a plus sign, and that's the Hamiltonian. So everything is consistent. Okay. So in the end, to summarize, we found that the quantity of interest U is n times this n, I'm bringing it back, times e to the psi n dagger psi n times the path integral d psi dagger d psi integral over all paths e to the I s of psi dagger and psi, where s of psi dagger and psi is integral of L dt from t0 to tn, and L is I psi dagger psi dot minus omega psi dagger psi. Okay, so that's our path integral. Okay, and from here generalizing to field theory is extremely simple. We just say that the corresponding, so this is a bit annoying, so let's write this factor out. What's this factor at the end? N is that, but I got e to the plus psi n dagger psi n. So finally I have e to the psi n dagger psi n half minus psi 0 dagger psi 0. So this is what we call a boundary term, and if we ever do a serious calculation with psi 0 and psi n being some different numbers in this odd Grassmann space, then we need to keep them. Okay, but in practice either we'll take the times t0 and tn to infinite past and future, then this term plays no role, or we are going to equate psi 0 with psi n when we try to do the finite temperature case, because as you know, in finite temperature we go to the Euclidean path integral and consider periodic paths. There will be a little surprise. It turns out that periodic paths is not the correct answer for fermions. Anti-periodic paths is the correct answer, and I'm about to derive that for you. 90% of references don't derive it, they just state it. It's like one of those big well-known facts of fermion path integrals, but I will derive it for you because it's always, it just keeps coming up without any warning. But first, are there any questions? Yeah.
Sir, if I increase the space dimension one by one,
Yeah.
will I get gamma matrix directly?
No, you won't get gamma matrix directly. We have cheated a little bit. We simply said that there's no, you won't get the gamma matrices automatically. So in order to get the space thing, you have to so the correct ultra-local limit of the Dirac fermion should keep all its 4 components, but just drop the del by del x terms. So the x dependence. But I should still keep it to be a 4-component object. Okay, it's just a pain to do that. If once we have done this, we can believe that we'll get such a path integral in every case. So the field theory path integral is just going to be the same, where S is the Dirac action integrated, Lagrangian integrated dt. There's nothing much to say about it except when we want to evaluate it. Good. Any more questions? Yeah, I realize this is all quite new, but once you get used to manipulating these numbers, as I said yesterday, they are very easy to manipulate, and actually this is a shorter set of steps even than the x of t case, where we had to do some Gaussian integrations and so on. All integrations in Grassmann variables are sort of trivial as long as you have finite number of variables. The real problem is if I have psi of t and x, my field, Dirac field, then it corresponds, I can do a mode expansion over space, and then there is an infinite number of Grassmann variables psi of t, like the one we have taken here. And then of course life is more complicated. So it's not that in field theory, fermion field theory, the path integral calculation will be so trivial, but it's quite trivial in the ultra-local limit. Good. Okay. So the last thing we want to do with fermions for now, So after the mid-semester, I will start discussing how perturbation theory arises from path integrals, and we'll see that all the Feynman rules and scattering amplitudes and everything, whether for bosons or fermions, will all be encapsulated by this formalism very nicely. And in that procedure, many things are simpler than with operators, and all these boundary terms and annoying things and the singular measures will all kind of drop out. So that's the part which all the textbooks do very happily, because the manipulations are very, very straightforward and they don't involve too much subtlety. Still, there are manipulations in the path integral language. Okay. But the other thing besides perturbation theory that we often do is to try and find the partition function using the Euclidean theory or imaginary time. And so we want to write z of beta equals trace of e to the minus beta h, where now h is the fermion, is this Hamiltonian, psi dagger psi. And this, we might guess, is integral d psi 0 dagger d. So what we should do is to take this thing where psi starts at psi 0 and ends at psi n, and we should identify psi n with psi 0 and integrate over the common value. So and of course make the time Euclidean, so the amount of Euclidean time is beta. It's the same procedure that we already did before. So this would be our normal guess. This is exactly what worked in particle mechanics. We simply took the paths to close. The reason they close is the trace. So trace means this state should be the same as this state, and we should sum over it. That's what trace of an operator always means, the sum of the diagonal elements. And diagonal is exactly this state being same as that state, and sum of those elements means integrating over the eigenvalues. So far so good. But now we can do a manipulation which is going to show us that something is not quite right. Okay. So for that, let's so what did I do here? There are a few inconsistencies in the notes which I will so this n factor, if I identify, so I'm going to work out this under the assumption that psi n is psi 0 and show you that something goes wrong. But under that assumption, these two factors are the same. So it's just a single e to the minus psi dagger psi, which is good because this exactly is what normalizes these states. So far so good. This is what I want to do. Now I can use this, I can evaluate this. I'm working in the operator language, okay? I'm simply going to show in the operator language itself that identifying psi n with psi 0 is not the correct way to calculate a trace for fermions. Yeah.
So the normalization for, like, so what we have done is we have taken the path integral and now we are integrating extra over periodic paths.
Yes.
So this n should be psi n dagger psi n minus psi naught dagger psi n, right?
No, because now we have the reason is that here psi n was introduced as a new variable which was not in the time slices, right?
Yes.
But now we are identifying psi n with psi 0, so psi 0 was already there. So what we did was, if you think of the time direction like this, and this is t0 and this is tn, then we sliced like this, and here we actually didn't slice, right? This was at the end. Okay, so the integration variables are 0, 1 times epsilon, 2 epsilon, 3 epsilon, up to n minus 1 epsilon only. Okay, but we introduced an artificial nth one which gave rise to this boundary term, this one. But now we are not going to do that. We are going to simply say that this is that. So there isn't an nth psi at all. That's exactly what it means to identify this with that. There's no independent psi n. So that's why that factor is not there. And in fact, the confirmation is that this is correct, because if you, I mean, correct in the sense correctly normalized, right? Because I want to calculate a matrix element of this between these states. These states are not normalized. I should normalize each of them, and that's the only way I should do it. So this is obviously correct. Even if I didn't remember that, this would still be correct. Okay. Now we can work out. So now we can do some. So the statement was that Grassmann integrals are very simple. So let's just do the integral. So this exponential is just that. And that expectation value I can calculate directly as 0 minus 1 psi 0 dagger e to the minus beta h, and then 0 minus psi 0 1. Right, I've just put in the explicit form of the position eigenstates which I had derived earlier. Now there's not much to be done except to manipulate the terms and perform the integral over psi 0 and psi 0 dagger. Since there's only one of each, here there's a bilinear. In the product between these states and these states, we have 4 terms: 0 with 0, where h contributes 0, then 1 with psi 0 dagger, psi 0 and 1, and then there are cross terms. But the cross terms have an odd number of psi. If I have an odd number of psis or psi daggers, the integral is never going to give me a non-zero answer. So I can forget about them right away. So I keep only the direct terms, and I get this 1 minus psi 0 dagger psi 0. And what do I have there? I have 1, and it's plus, and then I have e to the minus I omega beta.
Just beta.
Not just beta, omega beta, right?
Just
H is beta, H is omega. And sorry, I think I did that wrong. This 1, yeah. So 1 plus e to the I omega beta, that's exactly right. Except,
So to get the Hamiltonian
huh,
to the one number, you'll have
Yeah.
to flip the psi naught and the Hamiltonian.
no, Hamiltonian is commuting, so it commutes with even anti-commuting objects. So remember, that's the rule. Or even things commute with odd things, only odd things anti-commute with other odd things. Okay, but there's still an issue, which is that here I have 1 minus psi 0 dagger psi 0, and here I have 1 plus psi 0 dagger psi 0. And I still have to do the integral. Now when I do the integral, I either keep this and the 1 from here, or this and this thing from here. I can't take this with this because that's 0. But when I multiply these, I get 1 minus psi 0 dagger psi 0 plus e to the minus I omega minus omega beta psi 0 dagger psi 0. This 1 won't contribute anything because integral over d psi dagger is 0. So this is the full answer. But with a minus for this minus, and this comes with a plus. Now I can do the integral, and this will have to hop over this. So this minus will become a plus and I'll get 1. But that plus will become a minus and I'll get 1 minus omega beta. And now we have to stare at the answer and ask, is this the correct partition function? It looks wrong. Okay, let's retrace the steps why we got this answer. We got it because this we expanded, and this is certainly the correct normalization. Can't argue with that. Here we took the term minus 1 psi 0 dagger and minus psi 0 1. So two minuses cancelled. Psi 0 dagger combined with psi, 1 with 1 is 1. And so here we got a plus. Then we expanded this 4 terms, dropped the 1 and dropped the term where psi 0 dagger psi 0 is squared, because both of those, this one is anyway vanishing and the 1 vanishes under the integral sign, because fermion integrals of 1 are 0. So we are only left with these 2 terms, but this has a minus, this has a plus, and choosing our normalization, we get this answer. But if we had the reverse ordering here, I would have got minus 1 plus this. Both ways I'd get the wrong answer. One overall factor I can forgive, but this is definitely the wrong answer. And the right answer comes by saying, so psi n equals psi 0 was wrong. The correct answer is to take psi n equals minus of psi 0. That is to say, if the eigenvalue of the initial state was psi 0, the same eigenvalue of the final state is not psi 0 but minus psi 0. And that means that when we go to the path integral, it will have not periodic but anti-periodic fields. So they'll satisfy psi of t plus tau plus beta is minus psi of tau. And I'm out of time, but there's not much more to say. If I do this and I rerun my calculation, this turns into a plus and I have my partition function correct. And therefore, I can summarize the result by saying that the path integral, the Euclidean path integral for fermions which gives the partition function is z of beta equals integral d psi dagger d psi e to the minus Euclidean action of psi dagger and psi, but where the fields satisfy psi tau plus beta equals minus psi of tau, and then of course I integrate over the starting and ending points. So basically I integrate over all antiperiodic functions on a circle. And it's an interesting fact that antiperiodic, just as a basis of periodic functions is given by e to the I omega tau by, I guess, 2 pi tau by beta, right? If I add, e to the 2 pi n tau by beta, if I add beta to this, then I get this I. This is the basis of periodic functions. I can also take combinations to get sines and cosines. And the basis of antiperiodic functions is just shifting from n to n minus half integrals. Okay, and I've spelled out in the notes, and I think it's very easy to follow, that if I take this basis, then I'll get a determinant. Remember, the actual evaluation, this is a quadratic action, so this path integral is a determinant, and that determinant will give me not a sine function but a cos function, and it will precisely give me cos of omega beta by 2, which, as we saw, was the correct partition function of this theory. So everything fits in the end once we understand this. So it actually, this shift from periodic to antiperiodic enables this. Otherwise we would have got sine of omega beta by 2, and that would have been wrong, because sine would have e to the minus I omega by 2 minus of e to the plus omega by 2, right? So but in a partition function, every term should be positive. It's trace of e to the minus beta. Cosh. Thank you. Exactly. Cosh is guaranteed because we are in Euclidean. In the original harmonic oscillator, when we were in the normal real time, we were getting sine function when we divided harmonic oscillator by free particle. Here also, if we did that, we would get sine hyperbolic. But that was for open paths with some boundary or vanishing paths starting and finishing at 0. Here it's for all periodic paths. So a 2 comes in. This quantization basically has a 2 which was not there before. But this shift n to n minus half makes it cosh. So there's a formula which I've written in the notes, which you can, after factoring an infinite part from the determinant, the rest of it is cosh, and we are done. So I realized that this part went a little telegraphic, but first of all, it's in the notes, and secondly, there's not that much to do. After all this reasoning, the only new thing we learned was this. Otherwise, this path integral representation of the finite temperature or the thermal or the partition function, however you want to call it, is the same as it was for bosons. But always for fermions, it has a relative and it has antiperiodic boundary conditions strictly on time. Okay. Yeah, I realize that the last 2 lectures may have been a little intense, so maybe we won't include those in the exam. But up to Tuesday, we'll have everything, and good luck with the exam.